Let us talk about this interesting problem. We are given two strings. We need to check whether they are rotations of each other or not. We basically need to check if a string S2 can be obtained from string S1 by rotating S1 any number of times. We can either left rotate it or right rotate it any number of times. Let's see these examples to understand the problem. Let's say ABCD is our S1, S2 is CDAB. If I rotate S1 two times counterclockwise, then I'll get S2. First time I rotate, I move from A from here to here, I get this. Next time I rotate, I move B from here to here, I get this. Same thing I can get by rotating clockwise as well, right? If I rotate it clockwise, I'll move D here, then I'll move C here, right? So I'll get CDAB. In this example, S2 is obtained from S1 by doing one counterclockwise rotation. I have moved A from here, and I can obtain S2 by doing 4 clockwise rotations also. I move this A here, then I move this A, then I move this A, then I move B. So I'll get this, right? So if you're doing X left rotations or counterclockwise rotations, you can get the same string. If you're getting a string, then you can get the same string by doing n minus x clockwise rotations, right? In this example, these two strings are not rotations of each other. You can see by rotating string S1 any number of times, you will not get S2. If you rotate it once counterclockwise, you will get BA, BA. If you rotate it twice counterclockwise, you will get AB, then you will have AB, right? Then if you rotate 3 times, then you will have B, then you will have A coming here, then B coming here, then A coming here. This is what you will get after 3 rotations. So you never get this string. So these two are not rotations of each other. Now please pause this video, write down a function that takes 2 strings as an argument, returns true if the given 2 strings are rotations of each other, otherwise returns false. A naive solution to solve the problem is to try all n rotations one by one. So if string S2 is a rotation of S1, you can get S2 by rotating S1 n times one by one. First you rotate 1 times counterclockwise, then you check if it becomes same as S2. Then you rotate 2 times counterclockwise, then you check if it becomes S2. Then you rotate 3 times, then you rotate 4 times. So this solution is definitely going to take n square time, because you will be rotating n times one by one, and then you will be comparing 2 strings, right? So it's going to take n square time. Please note that this solution can be implemented 2 ways. You can either rotate n times counterclockwise, or you can rotate n times clockwise. Both ways you can get the answer, because every counterclockwise rotation is equivalent to a clockwise rotation. So this is an n square solution. Can you solve this problem in big O of n time? Let us now talk about an efficient solution. If you take a closer look at this problem, it's similar to pattern searching algorithm. We need to consider S2 as a pattern and S1 as a text, and we need to search S2 in S1 in a circular way. For example, if I want to search this in this, I can search C here, and then I can match D, and then it's the end of S1, so I'll go in a circular way. Then I'll match A with A, B with B, right? So I found S2 in S1. So I'll say S2 and S1 are rotations of each other. Similarly, if I try this example, the second example, I'll search for S2 in S1. I'll search for A, then I'll match for B, then I'll see a mismatch. So I'll not say this is a match. Now I'll look for next A and A match, B and B match. Now I'll go in a circular fashion, B and A do not match. So this occurrence of A is also not matching. So one solution is to implement our own pattern searching algorithm. Either implement naive searching algorithm, but that will be quadratic, or modify the KMP algorithm implementation ourselves and then implement in a linear time. But implementing KMP algorithm or any linear time algorithm would be a complex task. Here is a very simple implementation that's also a linear time solution. The idea is to concatenate S1 with itself. So instead of going in a circular way, we concatenate string S1 with itself, and then we use standard library functions which work in linear time. So what we do is we concatenate S1 with itself. So S1 now becomes ABCD, ABCD, and now if you search S2 in it, and if S2 is a rotation of S1, then it must be present in the S1 string concatenated with itself. So S1 plus S1 is ABCD, ABCD. Now if you search S2 in it, it's present here, CDAB. It is same as pattern searching algorithm in a circular way. Instead of going in a circular way, what I have done here is I have concatenated S1 with itself so that I can use standard library functions. Now if you see this example, I concatenate S1 with itself, I get ABAB, then ABAB again. Now if I search for ABBA in it, I won't find it, right? It's not there, so it's not a rotation. So this is how we implement this tricky approach in 2 lines. In fact, we can reduce it to 1 line by putting AND condition here, but it's 2-line implementation. The first thing that we check here is if S1 and S2 lengths are not same. If they are not same, then we return false. We check the next thing only when they are same, right? 2 strings have to be rotations if their lengths are same. And if lengths are not same, we return false. And if lengths are same, then we come here. And here what are we doing? We are concatenating S1 with itself. We are concatenating S1 with itself, and then we are searching S2 inside it using find function in C++ and using index of in Java. So index of function returns index of S2, index of first occurrence of S2 in S1 in this string S1 plus S1. And if it's not present, then it returns a negative value. So in Java, we simply call index of, in C++, we simply call find function. And find function returns a special constant string : npos if the string that you are searching is not present. Otherwise, it also returns index of the first occurrence. So we have 2 lines of code to check 2 strings are rotations of each other or not, and time complexity of the solution is also linear because concatenation will take linear time, and then searching a string in another string by these standard library functions also is a linear time solution. So this is a theta n solution, and it takes theta n auxiliary space because we are concatenating the string with itself to create a temporary string.